In this episode of Stemiverse podcast, Marcus and I talk with Karsten Schulz. Karsten Schulz, Ph.D, is an engineer, computer scientist and educator. He's leading the Digital Technologies Institute and is a designer of the B4 Modular Microprocessor for the classroom. Karsten has a background in the ICT industry, specifically in research and development. He's been involved in the digital technologies education space since 2008. Some of his previous activities include Young ICT Explorer and Bebras. Most recently, he designed and manufactured the B4 Modular Microprocessor, which students can experiment with in the classroom. Karsten is passionate about digital and biological systems, their similarities, and how things work deep inside. This is Stemiverse Podcast, episode 16. Welcome to Stemiverse, the podcast that helps educators become awesome at teaching STEM, be it at home or in the classroom. I am Peter Dalmaris, and with my co-host Marcus Schappi, our mission is to bring you the experiences of educators, students and stakeholders who strive every day to make the teaching and learning of science, technology, engineering, mathematics and art better. So here we are with Marcus in the Stemiverse studio. It's a studio right now.
It is.
And we are talking to Karsten Schulz, who is in Brisbane right now. We've got a lot to talk about with Karsten. And thank you for joining us in this for the next hour, Karsten. Really appreciate it. It's great to have you on. And we'd like to get started with taking a few minutes to introduce yourself to our audience. Tell us a bit about your background, where you're coming from, and then drive it all the way to today. And what is it that you're actually working on and what excites you these days?
Yeah, hello, and thanks for having me on your program. It's fantastic to be speaking with you today. So a bit of introduction about myself. I'm actually an electrical engineer, specialization in electronics. I'm also a computer scientist. As you can tell from my accent and from my name, background is German, came to Australia in 1999. I did study my electrical engineering in Germany. Then I worked for a large American software companies, actually computer software and hardware company. And then I joined the largest German software company in the R&D department. Then I moved to Australia in 1999 and worked for a cooperative research center, a so-called CRC. And then from 2001 to 2012, I rejoined the German software company, but in Australia, and established the Australian and Asia-Pacific research arm. So that included Australia, China, India, and Singapore.
You're talking about SAP, right?
That's right, yes.
Yeah.
It's only one large German software company that everybody knows.
The largest.
It's okay. We're not going to hold that against you. My wife has worked with SAP.
Hey, Apple uses SAP. Everybody uses SAP.
I think it's a great German conspiracy. I'm just joking here because the joke in the industry is so complex that you need to be a rocket scientist to figure it out. Sorry about that. We're regressing though.
So, but research and development for SAP. Yeah. So what did that entail? Because when you think about SAP, you think of, I guess, ERP, enterprise, resource planning, that kind of thing.
That is complex stuff.
But I'm sure SAP does a lot more than just that side of the coin.
That's right. And that was part of our mission to extend that. So we did a number of really cool things. We pioneered, often together with our university partners. So we built, for example, social media traffic apps that would read Twitter, put this through an artificial intelligence engine, and then spit out results that would then be put on a map. It was great. That was one.
Sentiment analysis.
Was the first app on the App Store for SAP at the time. My personal specialization is workflows, business process management. So I'm interested in the order and sequence of things and how things connect, right? How the control of things. We did even robotics. We did telepresence. We built, together with the University of Queensland, a very cool telepresence robot, which we used for video conferencing. So we could use that for our conference today. And that allowed the remote party to remote control that robot. So it expressed feelings and gestures like leaning forward, leaning back. You could actually shake your screen left and right. So if you were not agreeing with what was being said, you could shake your head, right? And then this remote robot would shake its head as well. It was pretty nice. As part of that, traveled the world, took me to a lot of interesting places, met with great people, and hold a number of patents as a result of this work at the SAP research department. So it was really cool and really interesting stuff. A number of things found their way into product. Other things didn't, but that was okay because not everything in research can become a product. But it really gave us a sense of how hard it is to take something from the initial concept stage and then turn it into a product that you then sell to the market. Yeah.
It's quite interesting for me, at least. Could you tell us a bit about what the environment is or was at the time in one of those SAP research and development teams? And in a nutshell, how would you analyze a problem, try to figure out what its components were? You've got an expertise in business process management as well, which probably comes in handy when it comes to analyzing the innovation process in the team itself. How was learning taking place?
Yeah, good. It was a great environment, very entrepreneurial environment. We had great partners in the universities. We had great partners inside the product department, and we tried to bridge that gap. We developed ideas, or often jointly developed ideas with partners, external, internal partners. We did rapid prototyping early on. I think we actually introduced agile development into SAP at the time. We started that in about 2001, 2002. We had a great team of engineers that we worked with. So the researcher would formulate ideas, develop them with the engineer, would turn them into code, iterate around that, involve the universities, involve the product department, and then bring this to a proof of concept, for which we would then make the decision of how we want to go forward with that within the existing SAP technology stack at the time. So a very, very entrepreneurial, engaging, always learning environment, meeting with great people who have great ideas and trying to put these ideas, make them happen. It's great.
Were those projects kind of secret? But you mentioned that I'm just thinking skunkworks of the US military now versus how things are normally done in a more organized way, hierarchical way. Were you like a member of skunkworks for SAP? Is the rest of the company like that?
At the time, yes. Well, they're both kinds of projects. Some of them were more visible. Others, we called them submarine projects. We kept going on them because we weren't quite sure in which way they would develop. Not because we wanted to keep them secret, but simply because we were not entirely sure which way to take them. And then at the right time, we then surfaced with them. So both aspects. Of course, in many projects, there's an element of confidentiality, right? You cannot talk about them at the time, especially when it's becoming part of a bigger project that's strategic for the company. But in most of our activities, we're actually quite open. And in most of them, we involved partners.
Universities in particular, or other companies as well?
Also both, yeah. Universities and other companies, yes. So especially in the context of European Union run and funded projects, we would have partners like, for example, IBM. They were part of some of our projects, right? So there was collaboration between the companies. We worked also with HP and their labs division.
Okay, awesome. So I don't know you from SAP. I know you from Young ICT Explorers, which I believe was a SAP-sponsored, competition?
Yes, SAP Young ICT Explorers is an initiative by SAP. I had the fortune of starting this in about 2008. Because I've left SAP, I'm no longer actively involved in Young ICT Explorers, but what I hear is still going, and it's going strongly. So I hear they've a large number of networks or locations now and reach a large number of students with that.
Just briefly, what is it?
What is Young ICT Explorers, the intention here is to reach out to the kids and give them an opportunity and an environment in which they can take pride in their work and showcase that to others. So the background of Young ICT Explorers goes back to about the year 2008. And at the time, we had a dinner at the University of Queensland. UQ was hosting a dinner, a teacher appreciation dinner, where the faculty was talking to the teachers about the things that were happening at the university. And I happened to sit next to a teacher, and we were lamenting the issue of why students are less and less interested in studying computer science. And the situation back then, I mean, we're talking almost 10 years ago, the whole environment was very different to today. I mean, today we've got heaps of competitions and maker spaces and maker fairs. And back then there was far less. And we felt that the students don't have an outlet where they can showcase their stuff. Compare this to, for example, sports. Every Saturday, students who are interested in sports can show what they can do, right? They go on the sports field, they play soccer and netball and cricket and the like. But back then there was nothing for the students in technology. So we set up this Young ICT Explorers, as today we would probably call it a maker fair, where students can, for as long as they like, work on a project of their choice. We said, well, we don't tell you what they should be working on or what technologies they should be using. We just said, do something exciting with technology, and once a year we meet and you showcase that to us. And that hit a nerve. Young ICT Explorers grew from Brisbane to Sydney, and then to Melbourne, and Hobart, and Townsville, and Perth, and Canberra. And it's a very nice environment for the students to come together and also look at what stuff other kids are doing, and get ideas. And we often find that students go back, and the day after the Young ICT Explorers event, they then start designing the next project for next year. So imagine that students working for like a whole year on their projects. That's something that you can't really do in the school environment simply because you don't have so much time. Yeah. But often schools combine that. Like they would say they've got a Young ICT Explorers work group at their school. So they use Young ICT Explorers as a carrot. But I should mention, I'm currently not actively involved in Young ICT Explorers.
Yeah, that's okay. No,
it's okay.
Because it segues into what you're doing today, which is...
before we get to what you do now, just
destroying my segue here.
Sorry.
That's okay.
But I'm going to kick it back. Going to kick the ball back to you. Since we are at the topic of Young ICT Explorers, I'm just looking at the website now, still going strong. It's been going on since 2010 at least, from what I can see here.
That's what the first one,
the
yes.
winners for 2016 have been announced. Is that a team sport? So do participants go into teams and then participate as a team in the competition?
They can if they want to. The competition is, unless it has been changed, I think it hasn't, for groups of up to 4 children. So Some kids prefer to work alone. That's okay. Or they can form teams, 2, 3, or 4 students. And that's great for teamwork and the like. But students can participate, I think, individually if they choose to do so.
Yeah. So I can see here that one team member has to attend a judging event. So you have rules, judges will look at the various aspects of the whatever is it that the team has put together and made, and then there's criteria to choose which one is the winner, right?
Yeah, like innovation, for example. How innovative is the idea? How difficult is the problem? And how well was it executed? And how well, very importantly, how well is documented and presented, right?
Right, yeah, because you need to support your work by submitting documentation in various files. There's documentation, there's video you can put in, iWorks here, PPP, presentation files, etc. So you need to substantiate what you're working on.
Just like real life.
Documented, yeah. Great. Do you think that social aspect is what makes science and technology, studying of science and technology, as fun as, say, playing soccer is on a Saturday?
Definitely. When you look at the kids there, yes. There's a lot of excitement and there's a lot of passion there. And I think it's an environment for those kids who are STEM-minded, who are doing great stuff, that they can show this to their parents and their teachers. Because the reality is often, like, if you do that stuff at school, for example, often you can't show it to very many people. Even if there are many kids around you, they may not be very interested in what you're doing. But all of a sudden you come in an environment where there are hundreds of other kids, like-minded STEM kids, and they say, wow, and I understand what you're doing, right? And I've got a few ideas of how you can take it further.
Awesome. So do you know of any other competitions like this around Australia?
Like that, I think the Crest goes into that direction, although I've never attended a Crest event. The various Lego competitions, they have got something like this. Although I think they're a bit more directed in terms of the topic and the technology. But yeah, they would be playing a similar division, similar league.
Okay, brilliant. So I should ask, what are you doing now?
Good question.
Okay, so at the moment, I now run a company it's called the Digital Technologies Institute, and the focus of the company is to help teachers get a really solid grip on computer science, because the reality is the foundations haven't changed that much, even in the last 45 years. There's, of course, a lot of changes on the surface and tools and apps and terminology, but the underlying foundations today are very much the same as they were, let's say, in the 1960s. Yes, computers have become smaller, which is great, so we can now carry them in our pockets rather than cheaper. Yes. But when we teach it to our kids, I think it's very important that we understand the foundations, because then that we really future-proof ourselves by knowing the foundations, what's happening under the hood, and that's what I'm interested in exploring and conveying to the teachers through the Digital Technologies Institute.
So how do you do this?
Yeah, look, we started in the institute and looking at the foundation of the foundations, and that is the inside of a computer. Okay, so I often tell the kids, okay, ask them who's got an electronic device, a phone, a tablet, or a laptop, or the like, and all the hands go up. Everyone says, yes, have got that. And then ask them, okay, who of you has looked inside one of these devices? And that usually brings the number down to maybe 20%.
20%.
Yeah.
That's pretty good.
Some of them have taken their own.
Yeah, you think that's good.
Yeah, well, it helps when your phone cracks and it splits open.
Yeah, okay. By accident.
And given that everything that we do, every mouse click, every keyboard stroke, every time we touch the touch screen, that goes through the processor. So I was really interested in exploring in how can we make that visible, because that is the central part of the computer. This is where everything is happening, all the action is, whether in the laptop, in a phone, in an iOS device. But we know so little about inside the microprocessor. So the thing that really annoyed me is I studied both electrical engineering and computer science, and I felt I knew too little about this device. And then because at the university we talk about logic chips, and we do AND logic and the likes. Fantastic. And then the next step is, hey, here's a processor, and now here's the assembler. And at no point was there a transition of how we now turn the logic chips into a machine that actually can add and subtract, and which can store information and retrieve it. I was always interested in how the immaterial becomes material, like when I press a key on my keyboard, right? How this then turns into some action that, for example, then a motor gets activated, which then closes a valve in a machine, which sits on the other side of the planet. We do have the technology, but I felt I never really properly understood it. And so I came across a really good book. I was recommended on Slashdot, and that is from an engineer from Microsoft. His name is Charles Petzold. I think the book was published in around 1999. It's called Code, the Hidden Language of Computer Hardware and Software. So I downloaded...
Is it code?
It's
Sorry.
code, just
CD.
code, yeah. Code, CODE.
Yep.
And I started reading, and I was really impressed because what Charles Petzold does is he develops very methodically from the bottom up the motivation of why we need these machines. Of course, knew that. But then also how you take these little switches together. And back then, and he says, look, we could have done this with relays in the 1850s, 1860s. Nobody made the connection back then. But he then connects these relays in certain ways, and we end up with an adder and maybe a bit of memory, and then we connect them in certain ways, and in the end, we've got a computer. And as I was reading the book, being an engineer, I had the technology here, I had breadboards and I had logic chips, so I started plugging these things together. Okay, and so as I went through the chapters, I built my little computer, and eventually I ended up with a big breadboard, a bit bigger than an A4 sheet of paper, convoluted with wires, but I had a computer. I had built my first computer. And I was really proud. And I showed this to a teacher, a friend, my son's friend. His mother came and visited, picked him up. She's a math teacher. And I showed it to her. She said, "Oh, this is really cool. We could possibly use that in the classroom." In brackets, but not with the wires. That's too hard. Imagining a student pulling out one wire and then all of a sudden nothing would work. So I sat down and turned the breadboard design into a printed circuit board design. Got the boards manufactured. I happened to have worked in a printed circuit board factory when I was a student. Earned a bit of money back then many years ago. So I called the owner, said, "Can we do that?" And he said, "Yes, let's do that." And did that, built it, assembled it, showed it to the teacher. We did a few design iterations, but that eventually led to a microprocessor. Yes, I've built my own microprocessor, which is modular, so you can connect different parts and run experiments with that. And that is what has resulted into this B4 microprocessor. So B4 is a little bit of an before we did the computing that we did today.
So, just to recap,
lots of questions.
So to recap, because that's all new stuff. So we in the maker space, at least, the maker revolution, a lot of what kids learn about electronics at the discrete level, say transistors, LEDs, resistors. When it comes to the microprocessor, there's the Arduino, so there's the black integrated circuit. There's a lot of magic happens inside, but that's as far as we go to analyze what's happening inside a computer. And same thing happens with the Raspberry Pi. You can see the breadboard, even more so. You can see the Raspberry Pi. You can see various components like the integrated circuits. There's the memory, there's the processor, there's a few inputs and outputs and the pins. But what you have done is to build an educational product where you can actually see inside that black chip in the middle of the Arduino or the Raspberry Pi and see how the microprocessor then works. Mm-hmm. Is that in a nutshell what you've done?
That's right.
That's what the B4 is?
That it is, yes. It is like taking the lid off a microprocessor, zooming in, and
keep on zooming in.
You're zooming quite a bit.
looking at the different parts, and each of the modules has a number of LEDs. So every module can tell you exactly in what state it is, what data is in there, and when you do that, and I'm teaching the B4 in the classroom here at St. John's Anglican College in Forest Lake in Brisbane. So I'm supporting the ICT teacher. And it's really great. Like just today, we did the binary number system. So we took just one of the modules out of the B4 kit, which is the counter, and we started to count in binary. Like we learned, the kids learn counting in decimal in year one.
I love binary.
So we counted in binary, and then we were running
it's so much simpler
challenge
than decimal.
Yeah, I would say so as well.
I think if kids learn binary first, they'll find it much easier to do pretty much any calculation that matters least than decimal system.
It's a good argument for that.
Should try that one day.
Yeah, maybe talk to the math teacher for year one. They think, but the idea is that you look. When I was at school, I came home and I had a little table, a little old camping table with electronic stuff. That was my lab, and I loved experiments. And I purchased electronics kits that I could get back then in Germany. They were really sophisticated. Imagine back in the 1985, 86, I paid $200 for an electronics kit. I have no idea what that would be in today's currency, but hey, a lot of money.
Yeah, it's a lot of money.
And the idea that you can do experiments and do it in a self-directed way not anyone telling you what you should be doing. You can branch out. That's the kind of learning that I like very much.
Do you have any formal? I understand now that you are supporting teachers in their work. Have you got the experience as a formal teacher or training even?
No, I'm not a formal teacher. No, I'm an engineer, but not an educator as such. No, not a accredited educator. No, but I work with teachers.
Yeah. So I'm thinking that the experience that you have in teaching really stems out of the way that you have learned how to learn. As a kid with your experimentation and your small lab with your kids. And then today we're now taking a problem and figuring out how to solve it and build a microprocessor on a breadboard essentially. And is that what informs you in the way that you teach today?
Yes, I think it does. Also an experience that I had in year 9. If you look at my school career, I was a brilliant student in primary school. Okay, and then
me too.
And then best student in year 4. Then in my state in Germany, we transitioned into high school in year 5. So I didn't have to learn much in primary school. Came easy. It got much more difficult at high school, and at that time only about 20% of a cohort would go to high school. All right, so it's a streamed education system in Germany. So all of a sudden you find yourself among more bright students, and the school expects you to learn. I hadn't learned how to learn. And I had a steady decline until year 9, when I almost hit rock bottom, got an E in mathematics. Can you imagine that? Okay.
Oh, wow.
Yes, almost.
Yes, I do. I believe that.
I almost had to repeat year 9. But that experience really taught me that I had to learn how to learn, which I then did. And I finished year 13. German high school went until year 13 back then. I finished again as best student. Okay, so my career is like an up and a down, a really low down, and then an up. So, and during that phase, I had to learn how to learn. I had my experiments, and I put all these things together and found the way that worked best for me, my learning approach. Okay.
Can I ask you, Karsten? Sorry to interrupt. What triggered, if you remember, because it's been a long time, but if you remember, what triggered those ups and then those downs? So what was happening in your mind or in your environment when your learning was going up like a rocket? And then what was happening when the opposite was taking place?
Foundations.
Was it people? Was it environment? Was it family perhaps? Problems that you had to deal with?
Oh, look, when you're about in year 8 and year 9 and you're in the middle of puberty, there are many things that you are not interested in, right?
Yes.
And other things you're more interested in. But what was always odd, like I was very good in physics, but at the same time I was poor in mathematics. And the school looked at this thinking, how can that be? How can you be brilliant at one and poor at the other? It turned out I was lacking the foundations in mathematics. Mathematics is one of the fields where you always have to stay on the ball, because every year something new is being added to the stack. And if you're lacking the lower layers, then it's really difficult to make connections on the upper layers. So I had to go back and relearn some of the lower layers.
Did you do that on your own, or did you have some help?
I had some help
from teachers?
My parents helped me with a tutor. And then we established the foundations, and then also we looked at what are my learning styles, what's the best way to learn. And you would be surprised, there's a lot of things that you need to memorize in mathematics. Mathematics is about logic, but not just. There's a lot of things that you have to learn by heart so that your brain can make the connections then on the higher levels and say, oh, these things are related, and you need to bring them together. So it turned out that by learning more about history, where you have to memorize a lot of things, I also became a better math student. So I'm actually a bigger fan of giving the kids more subjects. And like up until year 12, I think I have 10 different subjects at high school, and not to specialize them too early, because if you now take, for example, Math B and Math C and Physics and Chemistry, these are already 4 subjects out of year 6. So you're pretty much lopsided. I think it's not balanced enough. I think you get better education outcomes by giving the kids a wider range of subjects. So that was at least my personal experience.
So that's the logic behind that is in order to expose children to more stimuli, perhaps, and to stretch them a little bit more, right? And through stretching, you improve capability, tolerance, make them stronger.
Yeah, and I think trigger and use different areas of the brain, because they need to work together. It's one brain after all. It's not two brains or three brains that we have, which are compartmentalized.
So I was going to ask, teachers today, they're being taught how to do programming, let's say Python, and they get scared. And then you take them to Scratch and they're still a little bit scared. But you're going quite the opposite direction, going down to below the processor level.
You're going to electrons, not the bits.
Yes. How do you
try to scare them even more?
It would seem like that. How do you make this approachable for the teachers? How do you present it in such a way that they don't get scared?
Okay, so my core assumption is that over the last 10, 20 years, we've added several layers upon layers upon layers in computer science. That means that when you work in an environment which has a very nice, beautiful integrated IDE, you do things, but you don't really know what is happening inside the machine, which means that your learning experience is somehow limited. It's a little bit like in mathematics, right? If you do everything in the calculator and you don't solve any quadratic equation in calculus, then, well, you never really understand how it works. So I think there's an argument for removing some of these layers and going back to the basics. And even if that means that it is less colorful and less interactive, click and drag and drop. So by doing actually a little bit less, but doing this closer to the source, the learning experience is actually higher. And you can also trace problems much better. I mean, I've done visual programming in different languages. When everything goes right, it's fantastic. But if something goes wrong, you never know where the error really is, isn't it? Yeah.
Yeah. So how are the children that you are instructing in Brisbane, how are they handling the electrons and having basically to work in a bare bones system? No Scratch.
Not Scratch.
Just buttons.
Brilliantly. Last month we concluded the first 6 months of teaching computer design at the local school here in Brisbane, St. John's Anglican College, that I mentioned. And the kids have been responding amazingly. Look, we've been doing things, and the kids followed really well. Binary counting, we did addition, we did subtraction, doing subtraction by adding the binary inverse of the number. We learned about data storage and retrieval. We were coming to a point, and the kids did that. We did projects with them where we said, okay, build a machine that adds even numbers but subtracts odd numbers. Build a machine that adds an arbitrary number of numbers. Build a machine that just adds 3 numbers. And what really surprised us, the teacher and I, was that the kids came up with designs that I hadn't anticipated. So it's a little bit like playing Lego, right? You give the kids these pieces and say, do something interesting with them, and they come up with all these designs. And that's where we realized, yes, there's a handbook. I love handbooks. I think handbooks are great. So in the handbook, there are some instructions in there, and we teach the kids, and we follow that in the classroom. But in order to do these projects, the kids have had really to internalize a lot of the learning and then combine concepts, and they were able to do that. And that taught us, the teacher and I, that the kids actually can do a lot if we just let them. And that is like the design concept in Young ICT Explorers back from 2008. Just let the kids explore, just give them an environment and trust them.
So the lack of graphical point-and-click interface, did it have any effect, negative or positive, in your experience? Kids not having something to click on?
Surprise! Well, I gave them buttons to click on. So the B4 is designed interactively. It has buttons. It has dials. There are modules in the B4. It's a variable. I can give the kids a variable to touch. So not an abstract concept on a computer screen, but I can give the child a variable in their hand, and they can turn the dial and set the value of the variable. Because a variable is a hard concept for students to grasp, especially around the year 7 and 8. But if you can touch it, it becomes much more real.
So all that is implemented in a physical format, and will include pictures as well in the show notes. But just to describe now, it's a physical product. It's composed of various LED displays. There are various microchips that can implement memories, I suppose, or logic gates. There are input components, so buttons and dials. Mm-hmm. And it's a modular device, as you said, so you can plug various components into this processor. And then the children can use all these facilities to solve a problem, such as figure out how to get this thing to add two binary numbers together or to subtract and so on.
Yes, it's a physical product.
That's the idea.
Yeah. Tactile and interactive, yes. There comes the point where we connect it then to the laptop when we program it. It's connected to the Arduino IDE, so you can write code in the Arduino environment and then upload it to the B4. And there's a little component, a bootloader. I call it a hacking device because I also use it for cybersecurity kind of related tasks. So it can temporarily take control of the rest of the machine. And with that, the students learn also how to do a bit of cybersecurity if they're interested and if they want to. So it opens up quite a few opportunities.
What do you mean by that? Could you give us an example of the cybersecurity?
Yeah, okay. So for example, one of the current approaches that recently was discussed on IEEE is that if you're a hacker, you can hack into the sensor network, like the IoT network of a company. And if you manage to change the sensor readings so that what gets reported to the central decision system is somehow flawed, then the central server will make incorrect decisions, right? So it will, let's say, close a valve instead of opening it further. It's like the Stuxnet approach to some extent.
Just for our audience, can you explain what Stuxnet was?
Dear. I'm not sure. Is the CIA listening? Okay. So Stuxnet...
It's encrypted. Our episodes are encrypted.
So Stuxnet was reported to be, and I'm just basing this on publicly available information, so I've got no deeper insights than that.
We believe you.
And a virus that was infiltrated into the Iranian nuclear program to damage the centrifuges that would produce the enriched uranium. And what has been reported is that the virus changed the RPMs of the centrifuges so that they would break, whereas the monitor and control system still believed that the centrifuges were working within normal parameters.
Yep. So that's cybersecurity and how you can tamper with sensors and control systems.
Okay, so sorry, keep on going.
So you're getting the kids to do that now.
So the thing, this automatic programmer is a tool designed to, during the programming phase of the B4, take control of some components so that they don't interfere with the programming phase. But as they do that, you could actually say, okay, how do we now influence what the processor does? And for example, that 2 + 2 is no longer 4, but 5. What would be the consequence of that? So it's more an opportunity for the students to think about this than actually do real hacking. I mean, we don't want to educate them to bring down the cybersecurity network of Australia. But I think by being aware of these attack vectors, we are educating the future generation to take countermeasures in their design of software later.
Just the awareness aspect of this is important, right? We depend so much on technology, our phones, computers, emails. So being aware, Facebook, being aware of all these parameters of what our data or how our data can be tampered with. Tampered with. That's important on its own.
Yeah, it's a lot deeper than I thought you were going to go. I thought you were going to say, random number generator.
Random number generator. That's maybe the good idea.
Try that.
Yeah, okay.
So what age children are we talking about now?
About year 7 and up. So that's the 12-year-olds and older. That's about the age I'm aiming this at. Whereas the components of the B4, like the counter, which I've even taken into kindergarten and let the kids experiment with that which was fun. But
kindergarten,
yeah. But actually, the concept, the course of the B4 and building things, there comes a handbook like with 14 experiments that's been designed for year 7 and up. Yeah, and we've had kids there that looked at my designs and said, Dr. Schulz, there's a simpler way. Thank you.
Let me show you. Yeah.
And they did.
That's great.
And you know what? I updated the handbook with their designs.
Yeah, that's awesome.
Very
How
good.
are teachers receiving all this? Because, it's one thing to show a teacher how to do Scratch and upload it to a simple robot, but now going far deeper, and as you said earlier, the basics need to be there. So to understand how an arithmetic logical unit works, whether it is on a piece of paper or actually working in front of you need to understand a bit of binary logic. So I imagine that teachers will need to be somehow trained and brought up to speed with all those concepts before they can apply something like the B4 computer in the classroom. How do you deal with that?
Yeah. The way I've designed the lessons is that the students work more or less self-directed. So the teacher would give like a 5-minute introduction at the beginning of the lesson. Today we're looking at binary addition. But then the students can do most of the stuff themselves, and that's being then complemented by online videos, some of my own making, some of other videos that I found online. For example, James May from Top Gear. Hey, he has made a brilliant video about binary numbers. Awesome. Okay. Really? One of the best videos out there on YouTube. You should look it up. It's great. So I'm trying to make the life of the teachers a bit easier, and at the same time also give them the confidence that it is doable. And surprisingly, by removing these layers, you also remove complexity, as odd as it sounds. And you give the students a deeper learning experience, because there are a lot of branch points when we talk, for example, about a code in the B4. I like to make the connection about the code that runs in the cells of our bodies. And one little analogy that I like to use,
like a gene,
in the genes. That's right. So if I gave one of my cells to a forensic scientist, then she could extract the DNA from that cell. And that DNA strand is about 2 meters long, consists of 3 billion base pairs, which is an enormous amount of information. And then we look at...
There's a lot of junk in that, though.
No, actually, surprisingly, the scientists increasingly find that there's not that much junk in our DNA. Yeah. It's just that they haven't understood yet. You know, we thought the appendix was just junk, and then we realized that it actually has a purpose for our immune system, like the tonsils. So if we took the DNA strands from every cell in our body, and we've got 37 trillion cells in our bodies, so 37 trillion times 2 meters, that is 74 trillion meters, or 74 billion kilometers. Now, that is the equivalent of Earth-Pluto return 5 times. Okay? Tell that to your year 8 students. That will impress them. Okay?
Now they listen.
Now, we've got 37 trillion cells that at any given time of the day transpose and process code. Okay, we are walking supercomputers with free will.
Yep.
Okay, and then you talk about the concepts of computing, and that puts everything in a different perspective, because all of a sudden you've made the connection between digital technologies and biology.
Mm-hmm. That's actually a great argument for teaching children to, think of useful things to do with all these trillions and trillions of genes and cells in your body.
Yes.
It's like it really puts everything in perspective.
And there are now great videos that you can find on YouTube about the little molecular machines that work inside of our cells, that transport things from A to B, or that copy DNA. These little copy shops, they're machines in themselves. And the information to build these machines is stored in the DNA that they copy. So let's talk about a chicken and egg problem. You've got a lot of them inside of our cells, but it gets the kids. Evolution. It gets the kids to think about that and say, okay, but biological life is also not about computer science. It is information management, and we carry a lot of information inside us.
So in that way, you bring up an analogy between biology, our own bodies, and how this device on the table with the flashing lights relate to each other. They both process information and do something useful, or hopefully useful, with that information.
Yes.
Yeah, just this week, there was a paper about some scientists that encoded a video into DNA, and then were able to grow the cells, and then
Copied it.
Grab the DNA again, and then play back the video.
Oh, very nice.
So from a copied cell.
From a copied cell.
Oh wow! Yeah. Okay.
Because you can now go and synthesize your own DNA.
Incredible.
That's a few bucks.
It's the first step towards hybrids.
But just tells you how efficient DNA storage is, isn't it? It's tiny.
Yeah.
It's enormously compact, just about the quantum fluctuation level, and you can do so much with that. You can encode
And
life.
the copying efficiency as well is quite amazing. The way that the self-correcting copying of a cell into other cells for thousands and thousands and thousands of times. It's basically a digital system, very efficient and very accurate in those operations.
Yeah.
Wow.
A lot going on there.
So I'm looking at the time, and there's a few other things that we want to ask you in the next, say, 10, 15 minutes. So, for example, if there's one, maybe two people that are either dead or alive that have really influenced the way that you think, the way that you learn or operate every day, who would that be?
Probably my year 10 maths and physics teacher. He was a track and field athlete. So was I at the time. And he really, remember that in year 9, I had an E in mathematics. Okay. And so in year 10, I did really well under him, and he really rekindled my love for mathematics. So, if anyone,
how did he do it?
How? I don't know.
Yeah.
I don't know. The rest of the class didn't really like him. I thought he was brilliant. He had this special way. He was nerdy enough for my taste. He was digging deeper. He was not giving just superficial answers. He did the deep digging and satisfied my curiosity to understand how things worked.
So you were able to communicate with him perhaps in a way that you could not with other math teachers, right? And that brought you closer to mathematics. And
yeah, it was the right mathematics teacher for me at the time, yes.
Yeah. So that's important. I think everybody should be lucky enough to have at least one teacher in their life that really has an impact. So great.
Another person, if I may mention him, because we all know him, but Albert Einstein.
Yes.
And not just because he was a genius, but years ago I had the fortune to read his paper that he wrote in 1905 about the special relativity theory. And the way that he did this with natural language, he didn't use much formalism back then. And it so impressed me that a scientist can use just mainly natural language in order to lay the foundations of modern physics.
Yeah.
And I thought that's pretty special.
And I think that paper was also particularly short. I think just a few pages, where papers together, just academic papers when I was in academia, used to be 20, 30 pages.
Yes, and largely about formalisms, which nobody can read.
Yes, exactly. Oh my God. Where back then, things were very, very simple in terms of the length. Scientists wanted to be brief and to the point. So, thank you for that. Marcus?
I've got a list of questions here, and the one that I've got to ask you is, what is your programming language of choice? Because it's quite ironic, because what you're doing is you're not really doing much programming with your computer. Well, at least from a language perspective.
A higher level language. You use machine code, right?
Yeah.
10.11.10.
Yeah, binary.
Look, I've learned about 12 programming languages so far. Some more mainstream, some very, I don't think they even exist anymore, just experimental languages, that's right. But I think where I'm gravitating to when I have to solve something, it's C and its various variants, such as Objective-C or C++. So I find myself always drawn back to the C compiler, because then I can see what's going on.
Yep. That's the language of engineers.
Yes, it is.
Think.
Yes.
Do you have any applications that you can't live without? Applications that can organize your workload, perhaps help you remember things? Anything that you can't live, even email would be people's choice.
One app that I use every day, other than email and the normal word processing, is Wunderlist, which was a brilliant startup from Berlin. And I really like the way that they've solved task management. I think they're now part of Microsoft, but they still do a very good product. I still use and like it.
They're quite similar to Trello, aren't they? On the outside, it's like a to-do application, but it's quite complex or capable inside with processes and rules and all that.
Okay, I should look into that. I haven't used that yet.
All right.
I haven't used it for years, back when there was still an accelerator app. Do you guys remember Accelerator?
Oh, yeah.
You write in JavaScript and then it cross-compiles to, I guess, native frameworks on whatever target device.
I've moved through quite a few of these to-do apps. It's just complicated. Anyway. Marcus, any other questions?
Ooh, how should new educators get prepared for teaching STEM?
Okay, that's a good one.
Good one. Look, I think STEM needs to be experienced, cannot be taught, just taught. I think a new educator should develop a good repertoire of examples that demonstrate the application of STEM inside and outside of the sciences. So one example I love, for example, is how relativity theory by Albert Einstein, developed 100 years ago, now makes the global positioning system possible. I think that's the kind of example where it says, wow, somebody has done something, had no idea about its application at the time, but powered through, and now it's absolutely necessary. We all use it in our smartphones. We all have GPS chips there. So kind of these examples, I like them. Or
that's great, yeah. So experience, I think that's quite profound. Got to experience to know what it's like.
Absolutely.
So again, learning through doing, it comes out. Great. I think we'll stop about here, Karsten. So I'd like to ask you, just to leave, to stop the discussion here, if people that are listening to this podcast would like to get in touch with you and discuss any of the topics that you mentioned, and I think the B4 Computer is a great thing to talk with you about. How do they get in touch with you?
They can send me email or contact me on Twitter. They can find me on Google. Just type in Karsten Schulz or Digital Technologies Institute. My Twitter handle is KK no T, KKSCHULZ. And maybe you put my email address on your podcast website. So I'm very much looking forward to getting feedback and comments and thoughts.
Do you deliver workshops physically or online? If people would like to participate in one of those workshops and find out about your B4 Computer?
Sure, absolutely. Yeah, they just contact me for that.
Great.
Yeah, do that.
Awesome. Okay, great. Well, thank you very much, Karsten. Really enjoyed the conversation. And actually looking forward to have a look at your computer. I think next time I'm in Brisbane, I'll look you up.
Yes, thank you so much, Peter and Marcus. It's been great speaking with you. And thanks again for having me.
That's all for this episode. If you have any questions or suggestions, please send them to our email address, questions@stemiverse.com, and we'd be happy to answer them. Do you want us to interview someone in particular? Let us know. Visit us at stemiverse.com to get the show notes of every episode. And subscribe on iTunes by searching for the name of our podcast, Stemiverse. That is STEMIVERSE. Thanks for listening, and we'll see you next time.